for giving me the possibility to speak in front of you and to show new technology approach. I will also talk about value proposition for combined heat and power, so related to the process heat topic. And finally, our thoughts how to foster process heat application based on CSP in Morocco. So, few words to our company. The company is a very traditional company. It's an EPC company for power plants with a history of over 90 years. So the main businesses, the main segments, we say, are energy and power plant technology, so the classical EPC business, like combined cycle plants up to 150 megawatt. In Germany, most of the plants are built with combined heat and power. Decentralized energy supply, which is often applied in smaller cities with high flexible units, which are capable of following the transients in the grid, deriving from renewables. They are also combined heat and power plants, so we are really specialized in combined heat and power plants. Underground piping construction is also a business segment for district heating, district cooling, nuclear technology. As you know, we will phase out nuclear, so we prepare for making a business with phasing out nuclear. Let's see when this business will come, so we have more news in the newspaper than contracts. Industrial plants and construction, so we do maintenance in refineries, utility services like for automotive manufacturers like BMW, all the HVAC, heating, ventilating, air cooling, engineering and consulting, of course, and fabrication for large diameter pipes with inductive bending. The company has a turnover of 400 million euros and 2,500 employees. So the main parts of my presentation, I explained the technology of open volumetric receiver, then a value analysis for an example business case, and then a brief consideration regarding local content. So the technology I would like to show to you is a classical solar tower system, as you have seen in many presentations before. So what is the different part? Of course we have receivers, of course we have some energy storage, of course we have a boiler and a classical power block. But the main difference, and this is very important now, is that the hot part here is made of ceramics. So this means that the radiation and the hot air which we produce does only see ceramic material or ceramic fiber. What is the advantage of this? The advantage of this is that this part can very fast respond to load changes deriving from solar. So when we have volatile solar direct irradiation conditions, this system can very fast respond to a decline or to an increase of solar radiation. To give you a number, from 0 to full power of the receiver, we only need 5 minutes. And this is very fast. So this means, especially when you have harsh conditions or conditions located in an industrial area where you do not have the ideal direct irradiation, there you have the possibility with this fast reacting system to achieve the maximum yield in these different locations. Of course, the nicer the location, the better it is for the system, but this is clear. So I would like to show a video.
Kraft and Lagen München, KAM's concentrated solar power technology, an economic and highly flexible solution. Thousands of heliostats, designed to be manufactured locally, form a heliostat field. They reflect and concentrate sunlight onto a receiver at the top of a tower. It absorbs the concentrated sunlight, heating up to 1,000 degrees Celsius. The receiver consists of thousands of ceramic absorbers with an open honeycomb structure. A mixture of warm exhaust air from the power plant and ambient air flows through the absorber and heats up to 680 degrees Celsius. The hot air is used to fire a conventional steam power process. The process is operated at ambient pressure, ensuring maximum operational safety. The solid-state thermal storage is made up of simple ceramic bricks. It is a well-proven system with no hazardous or corrosive media, no phase change, and virtually no maintenance. Hot air heats up the bricks to nearly 680 degrees Celsius. By passing through the bricks, the air is cooled down to 120 degrees Celsius before it is recirculated back towards the receiver. During the day, the heat storage is charged simultaneously with electricity production. During intermittent cloud cover or at nighttime, production is ensured by discharging the heat storage. Energy production is decoupled from heat capture and storage. Volatile solar conditions do not affect it. Hot air from the receiver or storage enters a heat recovery steam generator, which produces superheated steam. Well-proven conventional power plant components guarantee maximum fail-safety and availability. KAM's CSP technology produces electricity on demand and dispatchable to the grid. Due to high process temperatures, state-of-the-art power plant components can be used in the water-steam cycle to maximize efficiency. At 120 degrees Celsius, the warm exhaust air from the heat recovery steam generator and the heat storage is recirculated. Most of the remaining energy is recovered by blowing the exhaust air in front of the receiver and drawing it back into the cycle. KAM's CSP technology, a simple, economic, and sustainable solution that provides solar power 24 hours a day.
Okay, coming back to the receiver. Here you see the modules again and the porous structure. So the whole receiver is made up of these ceramic modules. So it's non-pressurized. We have thin walls, and the ceramics allow us to accept changes in loads. And we, as I have said before, we are very fast in responding to variations in solar radiation. Then we also have large safety margins, so if we have a bad heliostat field with not an even distribution of the flux, we can allow hotspots due to the safety margin we have. And it's a very robust system, and the modular structure allows us, if we have any problems in the receiver, just to replace one module at night and then to operate the next day again. So it's not like to shut down for half a year a full plant. It's only to replace a module. So the heat storage is also made of ceramic ceramic bricks. It's a proven system, so this system is normally used to burn flue gases in industrial productions and to recover the heat of the burning process. We use ceramic bricks as a regenerator, and this system we just have applied to the solar tower system, which works very well. So we have no pressurized system, again, as I have explained before, no moving parts, almost no maintenance required, no risk of freezing, and we have a very low capital expenditure specifically. So we test a solar research tower plant in Jülich since 2009, together with the German Aerospace Center. And all the key characteristics, what I have explained before, are even more decisive for industrial process heat. Why? If you build a greenfield CSP tower plant, then you can fully concentrate and focus on the optimum electrical output. This is very different when it comes to industrial environments, because your client has already a main process and earns the money with the main process. So for the client at his industrial process application, the solar system is only an auxiliary process. So it's like IT or purchasing department. So he would not like to have any interruptions of his main processes deriving from a CSP system being connected to his main processes. So you have to adapt the system accurately. Then, moreover, the robustness is necessary. It needs to be easy, and so it must be possible that easy and short maintenance is feasible, and when you do not use the system, that you do not have any additional cost. For example, to heat molten salt or other systems to maintain the fluidized heat transfer medium. And finally, you need high reliability, efficiency, and availability to achieve your business case. So with this system, we believe we can add some value to such requirements of industry. So where are we now? Since 2009, we are operating the demo plant. Now we have the upscale of 10 to a 90 megawatt thermal receiver plant in Italy. And the next phase, the next step is a 360 megawatt thermal receiver for utility scale applications with a main focus of China and MENA region. So now comes the value analysis with regard to CHP applications. When we talk about new technologies, it's very important to consider the requirements to a new system. So it's very necessary that security of supply is assured. It's independently if it's a company having such a requirement or a state or ministry making tenders. Then the system must be economic viable, of course, and environmental friendly. So when we look to CHP, I have investigated some business cases what we have assessed in the past, and I created a typical business case to explain the value added of CHP. So what you see here is, for example, an industrial client having electrical demand of 10 megawatt and a heat demand of 17.9 megawatt thermal with a steam of 160 degrees C. So, and in addition, there's a site at the client where we can place a CSP tower. And with this tower, because the sites are often limited when it comes to industrial applications, can provide 26.7 megawatt thermal at a duration of 6,000 full load hours. So what you normally do is then you design a steam turbine and you have two options. Option one is to produce electricity only. Option two is to produce electricity and heat at the same time in cogeneration. So here you see the turbine. Here you see the input, the 26.7. It's very small. Coming from the solar tower, we make 7.7 megawatt electricity. Here you see the load case. So the electric power produced is 7.7 megawatt over a period of 6,000 full load hours, which is already good. But what we see, we have no contribution here with CSP on the process heat side. Option B is you have the same amount of live steam, so the same mass flow, and then you use the steam to produce electricity and to produce the steam as needed. So you would design the turbine to the thermal power demand of the process, to the 17.9 megawatt here of the load case. So, and then you see on the right side, you see we have a decreased electricity production compared to the electricity only case. Here we have 7.7, here we have 4.6. But we fully supply the heat demand, the steam demand, over a period of 6,000 full load hours. So from securities of supply perspective, the CSP system supports the provision of electric and thermal energy. When we come to economics, I investigated some numbers. So what is the electric tariff here provided by ONÖ? What is the cost of heat? So the price of heat, what I have considered, is lower than what was shown before in the factory, in the presentation, in the milk, showing the milk production case. And the total cost of energy without doing anything is 9.6 million per year. If you install a CSP installation providing only electricity, the cost of energy which you import from the grid and which you need to pay to the fuel supplier is decreased by 36%. And if we have the CHP business case, then we can decrease the cost for the utility services over 56%. This can be even more increased if we increase the solar tower capacity and if we would have more space. In this case, I would recommend this design because then the back pressure turbine is optimized to the process, and here the electricity you can supply, for example, economically also the residual load with PV. So there is a value added. This shows only the financial effectiveness. This does not show the financial efficiency, let's say. So payback period-wise, both cases would not be feasible, because the payback period would be more than 15 years. But the value added on the environment side, what you see is the reductions is in the base case you have nearly 80 kilotons of CO2. In the CSP electricity case you have 37, so minus 53%, and CHP minus 55. Why is this value so low compared to electricity? The reason is that we do not supply the residual electricity. We only supply the heat side, which is quite efficient in the process, because here on the heat side we have efficiency or boiler efficiency, a low pressure boiler efficiency of 85% to 90%, and only the rest substitutes the carbon dioxide, which is related to the existing production, electricity production in Morocco, which is around 700 gram per kilowatt hour. So with regard to the value added, CHP is technically feasible to provide a value added. Financially, it depends on the boundary conditions. So, the higher the fuel cost gets, the more financial feasible is a case, and this is also true for the electric prices. Now we come to what are the chances to foster combined heat and power with CSP. The chances lies in the total number which you would apply in decentralized systems. So instead of having, not instead, in addition to have 3 or 4 big large-scale units, like in Ouarzazate, you would have a lot of different units all over Morocco. And this higher number of numerous applications, its smaller investment volumes create a market environment. The market environment enables local companies to participate commercially. Why? Because big contracts are very hard to bear for small companies because of the requirements of bid bonds, liquidated damages, or warranty requirements. The more industrial, this approach would also foster more industrial research with university, creating innovations in companies, and gain of valuable know-how at international level by a variety of application. The industry is a very good partner to bear some of these challenges due to their know-how to absorb technology and to bear international commercial contracts. The NUR plants are a perfect showcase for the supplying industry to assess their own risk profile related to existing systems. And the CSP-CHP represents a switch from volatile fuel business to stable finance business, complying with the goals of CSP'23. And in these contract models or contracting models, providing combined heat and power systems at decentralized applications, it would be also possible to share some risks on the equity side with different major stakeholders in Morocco. So last slide. The open volumetric receiver suits perfectly for utility scale and decentralized combined heat and power applications based on its robust design. The decentralized CHP adds significant value to the energy policy triangle of Morocco. And decentralized CHP represents a complementary approach for Marsen, enabling significant increase of local content. So these were our considerations from a German perspective, and from my first visit to a CSP conference in Morocco. So maybe we can jointly improve business approaches and technologies together. Thank you very much.